Now, before we get to lenses, we just finished up with mirrors and spherical mirrors. We have to look at how a reflection and refraction will take place at a transparent interface. And of course, we've learned by Snell's law that the angle of an incident ray will change as we enter a higher index material. Typically, unless we're normal to the surface, the angle of refraction is going to be less than the angle of incidence. That's just Snell's law once again. So here's our angle of incidence, and here's our angle of refraction. Because the wave slows down as it enters the material with higher index, its angle is also going to have to decrease. Okay, how is that going to affect how something is going to look as it passes through this interface? How is something which is going to be immersed in this higher index material? Usually, the conditions that we use here would be for water, something immersed in water. How is that going to affect how it looks? Well, if we stick a pole into the water, what we notice is that the direction of the pole actually changes. So our expectation is if this thing is straight, this pole is going to just stay continuous in the same direction. But when we immerse it in water, we see something very different. We see that as it enters the interface, it appears to bend. Obviously, the pole itself is not bending, but what's happening here is, as we can see this, every point on the pole, which is now submerged, okay, the water coming off of that, or I should say the light coming off of that and propagating through the water, is going to change directions as it passes through the interface. The angle is going to become greater because we're going from a higher index to a lower index as we're looking at this pole, okay? So the pole will actually seem bent more in the shallow direction. It looks like the pole is bending toward the surface of the water, moving closer to the interface. Now, take, for example, the image of a coin, which is submerged. The actual coin itself sits lower than the image appears. So if you try to go down and grab that coin based on where you think the image is, you're going to go too shallow. Again, we can see why this happens. Here's the angle of incidence, okay? And the angle of refraction, we're going from a higher index material to a lower index material. The lower index material means that the angle of refraction is going to be greater. And if I trace that back in time, that places the image at a slightly lower distance than the object. So here, DI is less than DO. And we can actually come up with an equation for this. Basically, we're using Snell's law here. Snell's law says that N1 times sine theta 1 is equal to N2 times sine theta 2. So the sine of the angle is related to the distance of the object. Now, this is a little bit funny here. You would have thought that we'd use DI and DO here, but this is talking about the height that the object appears below the surface. And again, N2 represents the index of refraction of the material that we are entering. So in this case, it would be air. N1 represents the index of refraction of the water in this case. Okay, so that explains the optical illusion of why things appear to be shallower than they actually are. What happens when we have a spherical interface? And let me just say that we're going to a single interface here, because when we get to the lens, we're going to have two interfaces that we're worried about. Also, this is, as we'll see, a pretty good model for the human eye. So let's say that we have an object right here in front of the spherical interface with some radius r and some index of refraction n2, assuming that n1 is air, which is probably around 1. First of all, this object, in order to form an image, should be way, way to the left. But in order to get everything on the same diagram so you can see everything, we had to place it closer to the spherical interface. Usually, the distance to the object is going to be much greater than the radius curvature. But again, the way I drew this, I was sort of restricted. And you'll see what that creates a little bit of a problem in a little bit. But if that object is at that location, as the wavefronts enter the higher index material, they're going to get delayed most at the center. So the center of the wave gets delayed the most, and the outer parts would be delayed the least. And what this creates is a wavefront which is bent the other way, okay? It's now bent in this direction, and as it propagates, it eventually converges into this image right here, okay? So you can see we are going from a case where my light is diverging, it's diverging from that object, and then it hits the interface, and now we've got to be perpendicular to these surfaces, and it's kind of converge into this image right here. And again, this object should be way off to the left to be a more realistic situation. So let's do some more precise calculations right here. DL represents the distance to the object. DI represents the distance of the image from the spherical interface. And again, we have to obey Snell's law here. Here we have the normal direction to the surface, which is going to go through the center of curvature. And we have the angle of incidence theta 1, okay? N1 sine theta 1 is going to be equal to N2 sine theta 2. And that's going to create a convergence to our image right there. Okay, so here's our equation for that interface. Not an equation that we use very much, but we can see it has the index of refraction of both media, has the distance to the object, allows us to calculate the distance to the image based on the radius. So again, the way I set this up creates sort of a difficult situation, because for this image to form with the object so close, the index of refraction would have to be really, really high. And there are very few materials. Diamond or silicon carbide, which is moissanite, are the only things that are high enough to do this. But again, I was sort of restricted to how I could do this. So here's our equation. We plug in our numbers: radius of curvature 10 centimeters. Distance to the object is also going to be 10 centimeters. Again, normally the distance to the object would be a much larger number than that. We solve for DI, and here you can see DI equals 43 centimeters, and that's the location of the image there. Okay? I think the main thing to get here is that we see with this convex spherical interface, okay, it converges. It's a converging type of material. Cause the waves to converge, and if we have an object there, we will converge to produce an image within this. With two spherical interfaces, we can actually refract the light twice. Now, if this were reversed, oops, let me draw this a little bit differently. If this were reversed, so we had a concave surface instead, then what would happen here is parallel beams would actually end up diverging. Okay? If we're going from a higher index to a lower index, let's say we're going this way, parallel rays would converge. So when we get to the lenses, convex surfaces, whether it be the surface of the light entering or the light leaving, both are converging. They change the direction of the rays such that they tend to converge. Concave surfaces, entering or leaving, also tend to diverge the rays. But again, we'll see that in the following section. What about the eye? Well, the eye, in fact, is modeled pretty well, where we have the cornea being the main refractive surface of the optical system. And it's basically going from air to water. You know, it's pretty close to the index of refraction of water, probably about 1.4. But again, here we have our object. We trace a ray right here. It's going to pass through the cornea, and then that's going to cause it to converge to produce an image on the retina. Now, you know, when we look at the anatomy of the eye, we think, oh, lens, the lens is doing most of the refractive power. No, what the lens does is the lens allows us to change from, let's say, we're looking at something very distant where the rays are coming in parallel and they will converge to a point on the retina. Whereas if we're closer, it increases the refractive power just a little bit. So again, we'll get that image converging on the retina. We can only form an image that we can see when the image is projected onto the retina of the eye. Okay. So again, that is the eye as a spherical interface. And yes, the lens has a slightly higher index of refraction than the surrounding material, but it's not all that much higher. The lens is just there to change from near and far vision. Okay.